Stars begin their lives in very dense nebulae, huge clouds of gas and dust. It's very difficult to observe the process of star formation directly because the dust clouds block light, so we can't see into them. Still, we've got a pretty good idea how it works. Massive clouds can collapse under their own gravity, fragmenting into globules that become denser and hotter. These globules continue to collapse, eventually forming a protostar. A protostar still gathers mass from the gas and dust surrounding it. There's a competition between the gravity of the protostar, causing material to fall onto its surface, and the radiation emitted by the star, which hinders the process. Ultimately, the radiation wins and the star blows away the shroud of material, becoming a visible pre-main sequence star. Many such stars have protoplanetary disks surrounding them, made up of material left over from star formation. Planets form within the disk and eat up the remaining gas and dust. Meanwhile, the pre-main sequence star continues to contract, getting hotter and denser. The pre-main sequence phase and planet formation are over quickly. The increase in temperature and density of the star's core leads to the necessary conditions for nuclear fusion, marking the start of the main sequence phase. This is the longest phase of evolution for stars like the Sun, which will fuse hydrogen to helium for billions of years. The masses of stars are set at birth once the parent cloud dissipates. We observe a wide range of star masses, but low-mass stars are the most common. Our Sun is a yellow dwarf star, which are pretty common. More common are the red dwarf stars, which have less than half the mass of our Sun. Proxima Centauri, the closest star to us at just over 4 light-years away, is a red dwarf. For every one star like the Sun, there are 10 red dwarfs like Proxima Centauri. Intermediate mass stars are comparatively rare. For every 10 Sun-like stars in the galaxy, there's only one like Sirius A, whose mass is twice that of the Sun. But high-mass stars, with masses tens of times the mass of the Sun, are extremely rare. Only 1 in 3 million main sequence stars falls into this category. The lifetime of a main sequence star depends on its mass. The more massive the star, the shorter its lifetime. Massive blue stars like Spica live for only 10 million years. The Sun will live for 10 billion years, and most red dwarfs live for over 1 trillion years. What happens after the main sequence also depends on mass. Red dwarfs live a boring life, almost unchanging for their trillion-year lifespans, at the end of which they just fade into darkness. Stars like the Sun become red giants. In this phase, stars swell to very large radii. When the Sun becomes a red giant, it will be 2 astronomical units across. In other words, it will have expanded to twice the size of the Earth's current orbit. During the red giant phase, stars fuse helium in their cores instead of hydrogen, although some hydrogen fusion does continue in a shell around the core. Depending on the mass of the star, many different elements can be fused in this way, including oxygen, the very oxygen we breathe. The most massive stars can fuse elements all the way up to iron in successive shells around the core. After the red giant phase, intermediate and low-mass stars eject their atmospheres into space to become planetary nebulae. The name's somewhat of a misnomer from the 18th century, when astronomers thought these nebulae looked like planets. Although they're not actually related to planets, the material they eject into space will one day be incorporated into molecular clouds and become the building blocks of the next generation of stars and planets. At the core of a planetary nebula lies a white dwarf, a small, dense object about the size of the Earth. White dwarfs are the exposed cores of red giants after their atmospheres have been ejected. They are very hot, but not very bright, typically 100 to 1,000 times fainter than stars like the Sun. White dwarfs gradually cool and fade, radiating their thermal energy into space. High-mass stars do not end their lives as planetary nebulae or white dwarfs, but explode as spectacular supernovae instead. And although they look quite similar to planetary nebulae, supernova remnants, like the Crab Nebula, are made of quite different material. It is in supernova explosions that all the chemical elements heavier than iron are made. An object is left behind after a supernova explosion too, which in most cases is a neutron star. Neutron stars are extremely dense, typically 10 to 20 kilometers across, but with masses up to twice the mass of the Sun. Because of their densities, neutron stars have incredibly strong gravitational and magnetic fields. The random orientation of their magnetic fields in space leads some neutron stars viewed from the Earth to be pulsars, as is the case for the pulsar in the Crab Nebula. If the star is massive enough, at least 30 times the mass of our Sun, the supernova remnant could be a black hole, an object so dense not even light can escape it. An estimated 1 billion black holes exist in the galaxy, but they're very hard to detect. One of the best ways of detecting them is to look for the way their intense gravity distorts space and bends the light passing nearby. The supernova explosions that form neutron stars and black holes also eject several solar masses of material into space, feeding the next generation of star formation.